Assalamu alaikum dear students. I welcome you to 41st lecture of probability and stochastic processes. In previous lectures we have been analyzing Markov chains in terms of the behavior of different states in an asymptotic manner. That is, as the random variables in that collection we call Markov chain assume their values, how different states or different values behave. If a certain value is assumed infinitely often as the Markov chain evolves, that is, as we continue to sample this random unpredictable phenomena and observe the values of different random variables indexed with the sampling index, a certain value is shown again and again. The random variables, as they evolve, assume that value again and again, and as the Markov chain evolves to sampling instances approaching infinity, this state assumes its value infinitely often. If that's the case, such a state, such a value is called a recurrent state. And if a state is only visited finitely number of times before the evolution goes in such a way that it never visits that state again, that state is called transient state. We analyze the behavior of Markov chains in terms of transient or recurrent behavior through eigenanalysis. We looked at eigenvalues and eigenvectors of one-step transition probability matrix, which is also called stochastic matrix. So if a stochastic matrix has a unique eigenvalue of 1, then that Markov chain is a recurrent Markov chain and every state is visited infinitely often. On the other hand, if a stochastic matrix has more than one eigenvalues with magnitude 1, in that case these eigenvalues are second roots or cube roots of unity or fourth roots of unity, then this type of Markov chain is a recurrent but periodic Markov chain. We analyze the behavior of such periodic Markov chains by remodeling the graphical representation of Markov chain in a graph. And if the graph of a Markov chain was a bipartite graph, then this Markov chain had a periodicity of 2. And if the graph of a Markov chain was a tripartite graph, then it must had 3 eigenvalues with magnitude of 1, and this Markov chain was a recurrent Markov chain with periodicity 3. For recurrent chains, whether periodic or aperiodic, the n-step transition probability matrix either converges to a unique matrix or it converges to a sequence where the long-term n-step transition probability matrix usually circulates between 2 or 3 convergent destination matrices. We also used graph theory to analyze the behavior of periodic chains. The periodic chains whose n-step transition probability matrix does not converge to a unique matrix. In those Markov chains, the graphical representation of the transition jumps can be converted into an equivalent graph. And if in that graph there are only cycles with length 2, 4, 6, 8, etc., only even length cycles, then the Markov chain is periodic with periodicity 2. Such graphs were called bipartite graph. Similarly, if the state transition diagram of a Markov chain is converted to an equivalent graph, and that graph is a tripartite graph with cycles with length 3, 6, 9 or any other number multiple of 3, then that Markov chain was periodic with periodicity 3. Such Markov chains had n-step transition probability matrices that switched between 3 long-term values. In any case, for recurrent chains, either periodic or aperiodic, the n-step transition probability matrix never has such columns with all entries 0. there are always some non-zero entries. If it is an aperiodic chain, then the n-step transition probability matrix converges to a certain destination value and all the entries in the column are the same. And for the case of periodic Markov chains, the entries switch between 2 or 3 or possibly more values, but they are never all zeros. But when we analyze the behavior of Markov chains with some transient states, we found that in the long run, the n-step transition probability matrix has some columns corresponding to the transient states which are all zeros, representing the fact that in the long run we do not have any positive probability of finding our random variables assuming that particular state. If a state is transient, it only gets assumed by this sequence of random variables finitely many times, and afterwards it is not assumed. So for transient states, the long-term n-step transition probability matrix converges to such a value that columns corresponding to the transient states have all zero entries and columns corresponding to recurrent states have non-zero entries. We usually label our states in such a way that transient states are grouped together and recurrent states are grouped together, so that the equivalent n-step long-term transition probability matrix has non-zero entries in one section of the matrix. We are going to use this type of observations to further our knowledge of behavior of transient and recurrent states in finite state space Markov chains. So let's continue with a review of a few cases that we discussed in previous lecture and see how these ideas are applicable in those cases. The first case is where we had a Markov chain with only one recurrent state and all other states were transient states. You can see on your screen the graphical representation of state transition diagram of this Markov chain. Here the states are labeled from 0 to 5. There are 6 states and they are labeled in such a way that they are mixed. From 0 to 2 the states are transient, then state 3 is recurrent and state 4 and 5 are also transient. We should have labeled this Markov chain in such a way that this recurrent state was labeled towards the end, either 5 or 0. But in future references we are going to follow this convention. For now, this is reproduced from the previous lecture. So in this Markov chain, state 3 is recurrent state, all other states are transient states. It does not matter where you start, eventually you are going to end up at state 3 and then you are going to remain in state 3. If we look at its long-term n-step transition probability matrix, we see that it has a column of all ones corresponding to state 3, which is the recurrent state, and all other columns are zero valued. Hence all other states are transient states and only state 3 is recurrent state. It's also possible for a Markov chain to have more than one recurrent state. So if a Markov chain has a collection of transient states and other states are recurrent, then these recurrent states can be either in one group or in more than one group. So if this group of recurrent states is only one group, then Markov chain through its evolution, when reaches there, it gets trapped and never leaves that. An example of such a Markov chain was just shown to you, where state 3 represented that group of recurrent states where Markov chain gets trapped. It's also possible for a Markov chain to have more than one group of recurrent chains. So if the Markov chain starts from a transient state, it can either go to one group and gets trapped there, or it can go to the other group and gets trapped there. An example of such a two-group Markov chain was shown to you in last lecture, where we discussed random walk with absorbing ends. And one application of this random walk type of Markov chain was gambling between two people who have X and Y rupees. So if one of them wins everything else the other person has, then he has the total amount of money and the evolution stops. Similarly, if the other person wins everything this person had, then Markov chain stops. Let's have a look at that type of random walk with absorbing ends to see how the eigenvalues, eigenvectors, and other characteristics show up in the case of asymptotic behavior. The asymptotic behavior of transient states and asymptotic behavior of two end states, which are absorbing states representing two groups of recurrent states. On your screen, you can see the graphical representation of that four-state random walk with absorbing ends. So state 0 and state 3 represent two groups of absorbing recurrent state, and state 1 and state 2 represent transient states. If you look at the eigenvalues of this Markov chain, the eigenvalues of one-step transition probability matrix, they were 1, 1, 0.45 and minus 0.45. So it is important to note that there are two eigenvalues with value 1, or eigenvalue 1 has a degree of 2. This is going to be important when we analyze the long-term stationary probabilities of this Markov chain. Let's have another look at n-step transition probability matrix of this Markov chain and the value it converges to. It converges to this matrix, 4x4 matrix, which we have written P infinity, and this is long-term n-step transition probability matrix, and this is the destination value. And you can clearly see two columns with all 0 entries, and they represent the two transient states in the middle of the random walk. This is the end state on the right, and this is the end state on the left. So this n-step transition probability matrix tells us that probability of finding this Markov chain in state 1 or state 2 in the long run is going to be 0. No matter where you start, you will either end up at state 0 or state 3. Let's quickly look at a few particular cases where we start from a certain probability distribution and try to see where we eventually end up. The first case is where we start with initial probability distribution of 1, 0, 0, 0. That is, we start from state 0 for sure. In that case, the stationary probability distribution is same as the starting probability distribution, which also happens to be one of the eigenvectors. So if we start for sure in state 0, we remain in state 0 forever. This is also evident by looking at the state transition diagram. State 0 is an absorbing state. If we start in this state, we are not going to leave this state. We are always going to be in state 0. Now let's see what happens when we start in state 1. So if we start with initial probability distribution of 0, 1, 0, 0, that is, we start from state 1 for sure, then the stationary probability distribution is going to be 0.75, 0, 0.25. So if we start in state 1, in the long run, we will not be in that state, but will be either in state 0 or state 3, and ending up in state 0 has a probability of 0.75, and ending up and getting trapped in state 3 has a probability of 0.25. This is evident from this state transition diagram that if we start in this state with probability of 0.6, we are going to end up here in just one step, and with probability 4 we are going to end up in state 2 in one step. And then as the Markov chain evolves, there is more probability that we'll go from here to here and here to state 0 again and get trapped. Hence, probability of starting from here and getting trapped in the nearby state is much higher than probability of starting here, reaching here and getting trapped in state 3. So if we start from state 1, probability of getting trapped in state 0 is 0.75, represented by the long-term stationary distribution, and probability of getting trapped in state 3 is 0.25. Let's see what happens if we start in the next state. So if we start with an initial probability distribution of 0, 0, 1, 0, that is, we start in state 2, then we will end up with a long-term stationary probability distribution of 0.375, 0, 0, 0.625. If we look at the graphical representation of this Markov chain, then if we start from state 2, then getting trapped in the neighboring state 3 has a probability of 0.625, which is higher than 0.5. So if we start from 2, then with probability 0.5, we'll jump to state 3 in one step and getting trapped there. And it's also possible for this Markov chain to start from state 2, move to state 1, come back and then get trapped in state 3. Hence, if we start in state 2, probability of getting trapped in state 3 is 0.625 and probability of reaching state 0 and getting trapped there is only 0.375. The next case is when we start in state 3. So if we start in state 3, then initial probability distribution is 0, 0, 0, 1. With this initial probability distribution, the long-term stationary probability distribution is also 0, 0, 0, 1, implying that if we start in state 3, then in the long run, we will be in state 3 with probability 1. This is clear from the graphical representation of this Markov chain. State 3 is an absorbing state. If we start here, there is no other state that we can reach. We have to remain in this state for all future transitions. An interesting case for this Markov chain is when we start in one of the two states with probability values between 0 and 1. Suppose we start with this initial probability distribution of 0.5, 0, 0, 0.5. That is, we can start either from state 0 or from state 3, and probability of starting from state 0 is same as probability of starting from state 3 as 0.5. If we start with this initial probability distribution, we'll have the stationary probability distribution same as the initial distribution, which is also clear from the graphical representation of the Markov chain, that if we start in this state with probability of 0.5, we will remain in this state for subsequent observations. And if we start in state 3 with probability of 0.5, we'll remain here, and probability of getting observed in this state is same as probability of starting in this state. So if the starting probability distribution is 0.5, 0, 0.5, the stationary probability distribution is also the same 0.5, 0, 0.5. This is also applicable for other starting probability distributions where only positive numbers are for state 0 and state 3. For example, if we start with an initial probability distribution of 0.1, 0, 0, 0.9, we will have the stationary probability distribution of 0.1, 0, 0, 0.9. Let's see what happens if we start in these transient states with some probability between 0 and 1. Suppose you start with an initial probability distribution of 0, 0.5, 0.50, then the long-term stationary distribution is 0.5625, 0, 0, 0.4375. That implies that if we start either in state 1 or state 2 with equal probability, then probability of getting trapped in state 0 is higher then getting trapped in state 3. This is due to this unequal transition from state 1. From state 1, we go back to state 2 with probability of 0.4, and we go to state 0 with probability of 0.6. So once we are in state 1, probability of moving to state 0 and getting trapped there is higher compared to moving back and then either getting trapped in state 3 or coming back to state 1. Hence, if we start with equal probability in state 1 and 2, probability of getting trapped in state 0 is higher and probability of getting trapped in state 3 is lower. You can imagine if I change this number to 0.5 and this number to 0.5, how this long-term probability distribution is going to be. I leave this as an exercise to solve this Markov chain in terms of stationary probability distribution with these numbers replaced with 0.5 and 0.5. You should observe that if we start with this initial probability distribution with non-zero entries assigned to transient states, the stationary distribution replaces them with 0 and assign some positive numbers to the two recurrent states. You should also remember that this Markov chain had two eigenvalues with value 1 and associated eigenvectors of 1, 0, 0, 0 and 0, 0, 0, 1. We also saw just a minute ago that if we have an initial probability distribution of 0.5, 0.5, we get the long-term stationary probability distribution same 0.5, 0.5. Or 1, 0, 0, 0 also gave us a long-term distribution of 1, 0, 0, 0. That is acceptable, that is expected because 1, 0, 0, 0 is an eigenvector. Similarly, 0, 0, 0, 1 also gave stationary distribution of 0, 0, 0, 1, which is also an eigenvector corresponding to eigenvalue of 1. But we saw that if starting probability distribution was 0.5, 0, 0, 0.5, the stationary distribution was also 0.5, 0, 0, 0.5. And I told you that if it was 0.1, 0, 0, 0.9, then stationary distribution was also 0.1, 0, 0, 0.9. So why in this case there are more than one? Actually, infinitely many starting probability distributions which are of the form a number 0, 0, a number which remain the same. Intuitive answer is because these states are absorbing states, so whatever the probability of starting in these states is going to be the stationary probability distribution. But can we mathematically show that this is the case, that if we have a starting probability distribution with zeros in the middle and two numbers in the end which sum up to give 1, then stationary distribution is also going to be the same. Let's have a look at a slide. In this slide, the eigenvalues of one-step transition probability matrix for this Markov chain are 1, 1, 0.45 and minus 0.45. Let's assume that the two eigenvectors corresponding to these two eigenvalues are x1 and x2. For this particular case, they were 1, 0, 0, 0, that was x1, and 0, 0, 0, 1, that was x2. But they can be any other two eigenvectors corresponding to the two eigenvalues of 1 and 1. If we have these two eigenvectors corresponding to these eigenvalues, then x1 times p is same as x1 and x2 times p is same as x2 because the associated eigenvalue for these two eigenvectors is 1. Now let's take a general initial probability distribution and call it x and have it in the form alpha 0, 0, beta. So if alpha 0, 0, beta is initial probability distribution, it can certainly be broken down into alpha times 1, 0, 0, 0, that is the first eigenvector x1, plus beta times 0, 0, 0, 1, that is the second eigenvector. Hence, a starting probability distribution of this form x can be represented as alpha times x1 plus beta times x2. So any general probability distribution where middle entries are 0 and two end entries are non-zero, alpha and beta can be represented as same alpha times x1, the first eigenvector, plus beta times x2, the second eigenvector. If we take this general probability distribution and multiply it with one-step transition probability matrix P, we are going to have here in this bracket the representation of x that we obtained from the previous equation times P. Since this matrix multiplication is a linear operation, if you just follow the precedence, then this matrix multiplication with P is going to distribute, and we are going to have this alpha x1 times P plus beta x2 times P. And remember, x1 times P is going to be x1 because x1 is an eigenvector. Similarly, x2 times P is also going to be x2 because x2 is also an eigenvector. So if we replace that, then the result of x times P is alpha x1 plus beta x2, which is exactly same as x. Hence, if an initial probability distribution can be shown to be broken up into two parts, alpha times the first eigenvector plus beta times the second eigenvector, and these eigenvectors are corresponding to the two eigenvalues of 1 and 1, then that probability distribution is also a stationary probability distribution. This holds in general whether we have this type of eigenvector or some other eigenvector, because mathematically the result holds, and you can have a starting probability distribution which is a scaled sum of two eigenvectors corresponding to eigenvalue of 1 with degree 2 and get that probability distribution as a stationary probability distribution. We saw that if a Markov chain has a mixture of transient and recurrent states, then in the long run the Markov chain leaves transient states and gets trapped in recurrent states. If there is only one recurrent state, then Markov chain always gets trapped in that state. And if there are two absorbing states and they are also recurrent states, then it depends how you start. If you start in one of the two recurrent states which are also absorbing states, you stay there. And if you start from a state which is close to that state, probability of getting trapped in that neighboring state is higher compared to traveling to far away absorbing state and getting trapped there. And if you start with equal probability in the transient states, then probability of getting trapped in one state versus probability of getting trapped in other state depends on the transition probabilities which connect the inner transient states to outer absorbing states. So far, we have only considered the absorbing states, the recurrent states, to be of groups of just one state. Let's extend that. Let's have more than one states in the group which are recurrent and which are absorbing. So the whole Markov chain has some transient states and a group which is recurrent, and the whole group serves as absorbing group. So what happens in that case is shown in an extension of this Markov chain, and the graphical representation of that extended random walk type Markov chain is shown on your screen. This Markov chain that you are seeing on your screen is a modification of previous random walk type Markov chain where the two ends were absorbing ends. Here the state 0 has been changed. Now it's not an absorbing state, it is perfectly reflecting state. If you reach here, in the next step you will come back to state 1. But state 3 is an absorbing state, but it is not alone in this group. If this Markov chain during its evolution reaches state 3, then it is never going to go back to state 0 or 1 or 2. But if it is in state 3, it can go to state 4, come back, go to state 4, come back, or stay in the state 3 in subsequent observations. So this group of state 3 and state 4 is an absorbing group. Once you are in this group, you cannot leave. And once you are in this group represents a subsection of Markov chain, and this subsection represents recurrent states. State 3 and state 4 are recurrent because they get visited infinitely often. And state 0, 1 and 2 are transient because once you leave, you never come back to these states. Let's have a look at one-step transition probability matrix for this Markov chain. Please remember, state 3 and 4 are recurrent states and state 0, 1 and 2 are transient states. So this is one-step transition probability matrix that you are seeing on your screen. Have a look at the last 4 entries. This represent the transition probabilities from state 3 and state 4 to other states. And you can see that these two entries sum up to be 1 and these two entries also sum up to be 1. So this sub-matrix of 4 entries is also a stochastic matrix. State 3 and 4 were our recurrent states, absorbing states, and the sub-matrix corresponding to these two states is a proper stochastic matrix with row sum being equal to 1. Let's look at the sub-matrix corresponding to 3 transient states, 0, 1 and 2. This is shown here. If you look at this sub-matrix shown here, then the sum of entries in first row is 1, sum of entries in second row is also 1, but sum of entries in third row in this sub-matrix is 0.5 because other 0.5 has gone out, which represents transition from this group of transient states to this group of recurrent states. So this sub-matrix corresponding to the 3 transient states is not a stochastic matrix, but this sub-matrix corresponding to the 2 recurrent states is a proper stochastic matrix of size 2 by 2. There is a convention of putting the sub-matrix corresponding to the recurrent states in the top left-hand corner. That is, recurrent states are usually labeled first. If we do that, then this relabeled Markov chain is shown on your screen, and here state 0 and state 1 represent the group of recurrent states, and state 2, 3 and 4 represent the group of transient states. And if you look at one-step transition probability matrix of this Markov chain, you will see that in the top left-hand corner, the 2 by 2 sub-matrix is a proper stochastic matrix, and this lower right-hand corner 3 by 3 sub-matrix is not a proper stochastic matrix. Furthermore, for this group of 3 by 3 matrix representing the 3 transient states, if you look at the top part, the top sub-matrix above this sub-matrix, this is all zeros. The reason is that these transition probabilities represent transitions from these 2 recurrent states to these transient states. This 0 represents transition from state 0 to state 2. It's not going to happen because 0 and 1 represent a group of absorbing states. Once you are in state 0, you cannot go to state 2. Hence, this transition probability is 0. Similarly, from state 0, you cannot go to state 3 or 4. So all these transitions from absorbing group outside the absorbing group are 0. For the same reason, the transition probabilities from state 1 to state 2, state 3 and state 4 are 0 because once you are in state 1, you cannot reach back to these transient states. So if you have a mixture of recurrent states and transient states, we write the one-step transition probability matrix in such a way that the recurrent states are in the top left corner, and to the right of this matrix all entries are 0, and the submatrix representing the transient states is not a full stochastic matrix. It has something missing, and that something missing is shown here. Let's look at long-term n-step transition probability matrix. For this Markov chain, the long-term n-step transition probability matrix converges to this matrix, which has rightmost 3 columns with all entries being 0. These columns represent 3 transient states, and the 2 leftmost columns are non-zero entries, and they represent the stationary probability distribution that can be associated with 2 recurrent states. So if we start with any starting probability distribution, say 1, 0, 0, 0, 0, and multiply that with this matrix, you will get a long-term stationary probability distribution, which is shown here. So in the long run, probability of you finding this sequence of random variables in state 0 is 0.526, and long-term stationary probability distribution or finding this sequence of random variable in state 1 is 0.474. In the one-step transition probability matrix corresponding to this P infinity, this lower 3 by 3 submatrix represented the transitions between 3 transient states, and this top left 2 by 2 matrix represented transitions between the recurrent states. When you have taken the n-step long-term probability matrix and seen its destination, then you see that corresponding to that 2 by 2 submatrix, we have a stationary probability distribution type of matrix. So this is the convergent value of the 2 by 2 transition matrix corresponding to the 2 recurrent states, and this lower matrix of size 3 by 3 in lower right hand corner represents the destination of the higher powers of that submatrix representing the transitions between 3 transient states. So you can see that in the long run, the n-step transition probabilities between transient states has gone to 0, and in the long run, the n-step transition probabilities between recurrent states give you a stationary distribution of 0.526 and 0.474. This can be explained through proper partitioning of this one-step transition probability matrix that you can see on your screen now. Here I have partitioned one-step transition probability matrix P into 4 submatrices. The top left corner represents PR, the matrix corresponding to recurrent states, and to the right of this matrix we will always have zeros, because it's not possible to jump from this group of absorbing recurrent states to group of transient states. Hence in the top portion we have PR, the submatrix corresponding to recurrent states, and 0, and in the lower portion we have S and Q. Q represents the submatrix for transitions between transient states. So if we have partitioned this P in these 4 matrices, we can find higher powers of P shown as Pn, and they are going to be PR raised to power n. Here we will have 0, and here we have Q raised to power n. Here we have something different. I have not shown it as S raised to power n because this will not be the nth power of this S matrix below PR. This will be an nth version of this lower matrix, and it is shown as S with subscript n, not with power n. But this top left corner matrix will be nth power of PR. This lower right matrix will be Qn, which will be nth power of this matrix Q. And if you take higher and higher powers of this matrix, eventually you are going to get a P infinity, which will have zeros here and zeros here, because higher powers of Qn are going to be all zeros. And here we will have S infinity. Once again, it's not infinite power of S, it is just the destination value of this lower left matrix. And here we'll have PR raised to power infinity. So if PR, the top left portion of this one-step transition probability matrix, represented a full stochastic matrix, a submatrix which fulfilled all characteristics of a stochastic matrix, will have a stationary matrix here. And all the columns to the right of this matrix will be zero, and there will be some non-zero entries below this matrix, and they can be interpreted as probabilities of starting from transient states and moving to different recurrent states and getting trapped there. If we have a mixture of transient and recurrent states, the convention is to put recurrent states in the beginning and corresponding submatrix will be in the top left corner, and the submatrix corresponding to transient states will be lower right corner. Here we'll have zeros, and its infinite power is going to be of this format. In coming lectures, we are going to make extensive use of this partitioning technique, where we will partition this stochastic matrix or one-step transition probability matrix P into different matrices, like 4 matrices here, and then process these matrices separately. This matrix PR is just a stochastic matrix, and it will be processed similarly, but this submatrix Q corresponding to the transient states also has applications when we will be talking about the return times and other related ideas of Markov chains. You might be getting an impression that this PR raised to power infinity is going to converge to a unique value. That's not the case. This PR represents the collection of recurrent states and their interstate transition probabilities. If this group of recurrent states represents an aperiodic Markov chain, then this PR is going to converge to a unique value. And if this group of recurrent absorbing states is a periodic Markov chain, then this PR raised to power infinity is not going to converge to a unique value, but it will converge to a sequence of 2 or more matrices which get rotated, which get circulated as we take higher and higher powers of PR. This is applicable for a particular Markov chain we have been analyzing, that is the Markov chain representing the scenario of a person trying to perform Hajj. Let's have a look at the graphical representation of that Markov chain. Here, states 0, 1, 2, 4 and 5 represented the initial situation where a person tries to perform Hajj, applies and gets rejected and stays there. And once he jumps from state 2 to state 3, he stays in this group, which represents those people which have performed 1 or more Hajjs. So this group on the right side is a group of absorbing recurrent states, and this group on the left is a group of transient states. But I have told you that we usually label recurrent states starting with 0, and we label transient states with higher numbers. So if we rearrange these groups, then states 0, 1, 2, 3, 4, 5, these represent the recurrent group, and states 6, 7, 8, 9 and 10 represent transient state. I'm not going to show the one-step transition probability matrix or its higher powers or the matrix to which this one-step transition probability matrix is going to converge to, but if we do take the 11 by 11 matrix representing these transitions and take higher powers, we'll see there is a periodic behavior. There will be some columns which will be 0, but for the remaining columns there will be a periodic behavior. That behavior can be summarized as follows. The first thing that comes out of the eigen analysis of this 11 by 11 one-step transition probability matrix is that there are two eigenvalues of 0 and 0, and remaining 9 eigenvalues occur as cube roots of 3 numbers. There are 3 eigenvalues corresponding to cube roots of 1, 3 eigenvalues corresponding to 3 cube roots of 0.9798, and 3 eigenvalues corresponding to cube roots of 0.4466. The P infinity, the destination, has a periodicity of 3. So nothing converges to a unique value. If you take P infinity of the whole 11 by 11 matrix, it has a periodicity of 3, and there are 5 columns which are all zeros. These 5 columns represent the transient states. The remaining 6 states are recurrent states, and they make a tripartite graph. Hence, once the Markov chain is in this group of 6 recurrent states, it behaves in a periodic manner with periodicity 3. Similarly, there will be 3 stationary distribution with non-zero values for 6 recurrent states, but the values for 5 transient states will always be 0. So in the long run, the 5 transient states will have probabilities of 0, but the 6 recurrent states will have 3 stationary probability distributions, and these distributions will be assigned in a circular manner, 1, then 2, then 3, then 1 again. So all these things are expected from a Markov chain which has some transient states and some recurrent absorbing states, but these absorbing states are forming a tripartite graph. In today's lecture, we extended our treatment of asymptotic behavior of Markov chains in terms of transient and recurrent behavior. We analyzed transient states and recurrent states through eigenanalysis and through other techniques. And we saw that if a Markov chain has a mixture of transient and recurrent states, then eventually it's going to have a situation where the Markov chain reaches the group of recurrent absorbing states, and then it's going to stay there. Hence, in the long run, probability of this Markov chain assuming values into transient states is 0, and the probability of this Markov chain assuming values in recurrent states depend upon the number of states and their interconnectivity. It's possible to have a unique long-term probability distribution where entries corresponding to transient states is 0 and entries corresponding to recurrent states is a fixed unique set of numbers. But it's also possible to have a situation where the long-term probability distribution has zeros corresponding to the transient states, and corresponding to the recurrent states, the numbers circulate in 2 or 3 distinct values depending upon the periodicity of the group being represented by recurrent states. In next lecture, we are going to analyze these Markov chains in terms of return times and expected number of visits during finite and infinite observations of the evolution of Markov chain. Till then, I wish you the best. Thank you. Khuda.